In the next series of lectures, what I want to do is start to analyze moving charges. We'll start with the simpler case of a moving point charge. And this is what we're going to work out is something called the Leonard-Weichert potentials. Okay, and so let me lay out the scenario for it. So let's imagine that we have our coordinate system right here, and the position of my charge is going to follow this trajectory, which I'm going to label as W. So W is a function of time. So our charge is going to start at this position. So if you measure it from the origin, that position is essentially what you get from this function W. And what I want to measure is I want to measure the potentials at some point R. And so what I can say is that the difference between where the charge is and where I'm going to measure the potential is script R. Okay, so later on, at some later time, the charge is going to move down here to some position here. So right now I'm taking a snapshot and saying what is the potential at the position R at this time t, given what I know about the path of the charge. So what I can do is I can write down the retarded potential like so. And what I'm going to say is that at this one instant in time, that position R is pretty much going to be fixed. So I'm going to pull it outside of the integral, like so, and just deal with integrating over the charge distribution. Okay, so now what I have to consider is basically the volume of what I'm integrating over. So I'm integrating over the volume almost like of a stationary point charge. And so, no, well, no, sorry, not a stationary point charge. I'm integrating over a point charge. And so if I think about it, a point charge doesn't really have a volume. By definition, it's a point. So instead, what I'm really considering here, which is one reason why I pulled the 1 over r outside the integral, is I'm actually integrating now over the charge distribution of what the charge maps out. So this charge it's a point charge, but it's moving over a distance. And so as it moves over a distance, my observation is that it kind of is it spreads the charge distribution out a little bit. And so if you want to consider what's going on, I essentially have some length L, and then this length L is moving with the velocity v, and essentially extends out a length L prime. And so if I look at now my distance, how it's being mapped out, I have this distance, this unit distance, r hat. And so what we have is that basically you have the map of the charge as it moves through time. It's filling up this volume of space. So that's the charge distribution that we're going to try and analyze. It is not the charge distribution of a single charge, but basically the charge distribution as it moves out in time. Okay, so if I take a look at this, then anyway, that the the extra distance that the information is traveling, it travels at the speed of light. So what I could say is that L times the cosine of theta divided by the speed of light is the same thing as saying L prime L over the velocity v, how much my length is moving. So therefore, I can write down the length L prime as L over 1 minus v cosine theta divided by the speed of light. Okay, so if you work that out, that should be true. Basically, this length is stretched out only in the direction of the velocity v. And so my volume becomes the original volume divided by 1 minus r hat dotted into v divided by c. So, the r hat dot v, it gives me is my component of v in the r direction. So that's the magnitude of v times the cosine of the angle theta. So that's how I was kind of able to generalize the v times cosine theta into the dot product. So this is my volume mapped out by the charge. And so now if I put that in, basically define the charge distribution, so d tau prime, I get q, the charge, minus 1. So basically, it's the point charge q modified by this volume term, is what you get. So we've now integrated over that, and so what I get for the electric potential is a 1 over 4 pi epsilon naught 1 over r q 1 minus r hat dotted into the velocity v, with which the charge is moving with. So what I could do is multiply through that that r, and so what I get is 1 over 4 pi epsilon naught q over q times c rc minus r dot v. Okay, so let me explain exactly what I did. So in this case, I multiplied the numerator and denominator by c. So that gives me a c in the equation in the numerator right here. And then I also multiplied through by r. So that gives me my r times c. And this last part here is I changed from r hat to just the vector r, because remember, by definition, r hat is r arrow divided by r. So therefore, I just changed that around. And it left me with the dot product now of r dot v. Okay. So that is kind of interesting. So let me rewrite it so I don't have all the circles in there. So my electric potential now at some position r in time t is 1 over 4 pi epsilon naught q times c over rc minus r dot v. So that's kind of interesting because it looks like a Coulomb's law potential, and it would be if r dot v goes to 0, then we would get Coulomb's law. So if we have a charge that is stationary, if v is equal to 0, then we just get Coulomb's law. Like so. Okay. Okay, well, what about the magnetic potential? So for the magnetic potential, the current is now defined as the charge distribution moving with some velocity v. So we can put that in, and so the potential A is mu 0 over 4 pi. Now the velocity over r. So all those things I can take outside of the integral, and I'm left with the charge distribution integrated over the volume. Exact same integral that I had before. So now if I plug in the result for this, what I get is mu 0 over 4 pi, the velocity, divided by r. Oh, I'm sorry. Yeah. So I get, well, I might as well just put it in. So I get, 1 over r. So then this gives me q over 1 minus r hat dot v over c. And when you do the exact same math we did before, we multiply the numerator and the denominator by c. We multiply the r through into the parentheses. What you get is mu 0 over 4 pi q c times the velocity divided by rc minus r dot v. Like so. Okay, so that's kind of interesting because what we have now is we have velocity-dependent potentials. So our potentials now depend on the velocity of the moving charge. So that's good. It takes that into account. And for the magnetic potential, the interesting thing is that we have essentially a current created by the moving charge. So Q is essentially our current. And so if we were to actually think of the static case, which would be kind of weird, but if you think of the static case, say if V was 0, then you wouldn't have a current and you wouldn't have a magnetic potential. So, so these are the Linear-Weichert potentials, where we now have rewritten essentially what were our Coulomb potentials for a point charge, but now they are velocity dependent, so this point charge can now move through space, and we can still calculate the electric potential and the magnetic potential.